Hi everyone. In this example, we're going to work on another application of exponential functions type problem. In this one, I'm going to give you information about how fast a colony of bacteria is growing or decaying. And I would hope that when we're given that information, we would be able to write up the equations. That's what we're going to practice here. So my goal is that if I give you an equation, you should be able to tell me what's going on. If I give you the explanation of what's going on, you should be able to give me the equation. So I'm going to use two variables all the way down just to make life easier. Let's say B is the number of bacteria, and what are we using for time here? 20% each day. Let's say that D is the number of days. So we have a time variable and a population variable. And now we need to start working on writing a B of D formula for each one of these. Okay, so B of D, if we have a colony that starts at 30 and increases by 20% each day, increasing something by 20% means you multiply it by a 1.2. So this is an exponential type pattern. For every day that passes, we multiply by another 1.2 to end up with the 100%, all of what we started with, and an additional 20%. For exponential, we're working on this y equals a b to the x type format. The A is going to tell us the initial amount, the y-intercept. So here we had an initial amount of 30 ants. The B is going to tell us what we're multiplying that 30 by. We've already decided that we're multiplying the 30 by a 1.2. And this happens once per day, so just a plain old D goes up in the exponent. So again, this is just understanding this form of exponential equations. Initial amount, growth or decay rate is shown in the base, and then there can be time information, how often it happens up here with the x. Okay, sorry for yawns, letter B. We are looking at a different colony that starts at 13,500 and decreases by 8% each day. Okay, so if you want to decrease something by 8%, you have to multiply by 0.92. If something decreases by 8%, we end up with 92% of what we started with. So multiplying by 0.92 will give us the 100% that we started with minus the 8% that we're decreasing. So we need to start with 13,500, and we need to multiply that by 0.92 to the D. It happens once per day, so a plain old D once again in the exponent here. Okay, so for part C, we have a colony that starts at 200 and increases by 12% every 8 hours. So this is the tricky part of this one. We've defined a variable to be number of days, and now we have to decide what that tells us if we're given information about what happens every 8 hours. Starting amount is still pretty easy. That just goes right out in front. If I want something to increase by 12%, I need to multiply it by a 1.12. And here's the tricky part. I don't want it to happen once per day. I want it to happen every 8 hours. And since we're working with days as our units, I would say 3 times per day, or every third of a day. Either way you want to say that one. If I want something to happen 3 times per day instead of once per day, I need to take my D and I need to multiply it by 3. It's going to speed it up. So when D equals 1, I'll have 1.12 to the third, which means it's already, after 1 day, increased by 12% 3 times. Okay, part D, a colony starts at 13,800 and decreases by 350 per day. So 13,800, that's a starting amount. this information, most important thing for you to spot here is that this is not describing an exponential relationship of any sort. I'm not multiplying by something over and over and over again. I am subtracting something over and over and over again. So I've been given my b value, my y-intercept, and if this decreases by 350 per day, then that's my slope. So 13,800 minus 350d. Okay, we're getting close. A couple more that I want to make sure I talk about. Part E, the colony starts at 750 and doubles every day. Okay, so I want to mention two pieces of vocab. One of them came up here. Doubling time. I didn't word it this way, but I could. I could say a colony starts at 750 and grows with a doubling time of 1 day. Doubling time directly translates to how long it takes to double. So if you are ever told that something has a doubling time of 2.5 hours, that means every 2.5 hours that pass will cause it to double. So doubling, that's multiplying by 2. So I'm going to say that my A is 750, start at 750 bacteria. Doubles every day means we're multiplying by 2. Since it's every day, we're just going to put a plain old D up here. If it was every 2 days, we would put a D over 2 up there to slow it back down. Okay, so doubling time is one little piece of vocab that you should be aware of. I would expect you know what that means if it comes up on a test. The last part of this one has a colony that starts at 1 million and decreases with a half-life of 1,000 days. Okay, so this is one more piece of vocab. If you see half-life, that is directly translated into how long it takes to cut in half. So if you start with 10, the half-life would tell you how long to get from 10 down to 5, and then from 5 down to 2.5, and then from 2.5 down to 1.25, and so on. So this says we're cutting in half every 1,000 days. Cutting in half is a multiplication, so this will be exponential. So we'll stick our starting amount out in front. We are multiplying by 1/2, but we're not doing it every day. It doesn't cut in half every day. It cuts in half every 1,000 days. So again, I hope you're starting to spot that that 1,000 is going to go up here in the exponent with the D. And then I think the thing that gets a little tricky is deciding if you should multiply or divide by the 1,000. So here, if I try, let's try that, dividing by 1,000, remember the division like that should slow it down. So that's why I'm making that be my first guess. But you can also try and pick nice D values to see what's happening. So for example, if D is 1,000, then I just get half of 1 million, which means after 1,000 days, it did in fact cut in half, which matches up this half-life of 100 days that I have. All right, thanks for watching.